All right, we're going to do one example that combines some things that we've learned previously with our correlation coefficient work. If you look at the data here, or the example problem, it should be a little bit familiar. I think I used this as a warm-up a few class periods ago. So if not, then let's just take a look at it here and see what we can do. So the example is a biologist is studying the relationship between a tree's diameter and its height. She records the following data for 7 different trees. Use Desmos to calculate the line of best fit equation. Write it below, round to 2 decimal places. All right, so let's do what we have done before with Desmos, kind of like we practiced over the last week in the last number of sections. Let's see if we can delete off what we have. All right, we're going to add in a table here. And we got 2 through 8 for the diameters. So 2, 3, 4, 5, 6, 7, 8. And then we're going to put in our heights. See if I can get a little bit more workspace here. We've got 8, 10, 16, 17, 22, 20, 29. Okay. So you can see our scatter plot. Again, x would be the diameter. Remember, diameter, for you guys who aren't as familiar with that term, but diameter is the distance across a circle. So if you imagine a tree, right, it's going to, if you look at a tree and you're looking at the, down through the trunk of the tree, we're looking at how far across the tree is. All right, so that's the diameter. And then, of course, the height of the tree. All right, so we're going to then do a line of best fit. So we've done this before. We're going to do y1, and use the little symbols that we have, equals mx plus b. I went through that a little bit fast, but we have done that a last number of days, so I'm going to spend a ton of time talking through every keystroke there. But we have now our line of best fit. I'm going to actually bring this over. I'm going to, just like we've done before, I'm going to drop this in, take a screenshot of it, and drop that in to our notes. Give you a whole lot of space on the top of the page here. So we're just going to drop it down here on the bottom and reference it as needed. All right, so first question was use Desmos to calculate the line of best fit. Write it below, round to 2 decimal places. So recall, once we do that, we have the slope here. And we've got our y-intercept. So we'll do something like 3.18. Y equals 3.18x plus 1.54. All right, what is the slope? State the meaning of the slope. So recall, 3.18 is our slope value. What does it mean? For every 1, and what's on our x-axis? What's our x? Remember, x is the diameter. So for every 1 inch diameter, the height, because that's our y value, is increasing, because our slope is positive, is increasing by 3.18 feet. We've practiced that a few times. Hopefully that makes sense. The y-intercept. So the y-intercept value here was 1.54. Remember, y-intercept on a table is across from 0. Now, we don't have 0 on our table, so we're going to have to interpret this. So our y-intercept is 1.54. And so that means for a 0-inch diameter tree, the height is 1.54 feet. All right, now that doesn't make a whole lot of logical sense. This is one of those extrapolating back to the y-intercept. A 0-inch diameter means that there's no diameter, so we're going to have at least some positive value for the diameter for it to have any height. So that doesn't make as much logical sense, but that's literally what it would mean. Okay, so the new thing here then is, what is the correlation coefficient? Notice we didn't plot the residuals this time, because what we really are going to start referencing now is the R value, the correlation coefficient. So there it is. It's been there all along. So that's our correlation coefficient. And that's going to tell us how linear our relationship is, how closely correlated, and what direction the points are. Now that 0.96, R value, is about 0.96. So that means that there's a strong positive correlation. That's really close to positive 1, meaning the points are pretty close to the line. There is a strong positive correlation because it's close to positive 1. Remember, the correlation coefficient goes between -1 and positive 1. The closer it is to either -1 or positive 1, the more linear it is. This is close to positive 1. So it's positive correlation between the two variables, in which case the two variables in this case are the diameter of a tree and its height. That should make some logical sense, right? As the diameter, as the distance across the tree grows, so should the height. All right, it would be unusual for a tree to grow sideways but not to grow up. For people, that might be something that is more common. There are people as they get older that grow more sideways than up. So maybe that's true for our diameters. We'll see something a little bit different. But for trees, not so much. As the diameter goes, they generally grow taller. Although I think they probably do level off at some point. Hopefully that makes sense, and now we can see where we see that correlation coefficient in our work on the linear model.